So now we're going to continue with the next phase of glycolysis, which is steps then 6 through 10. So in the second step is what leads to the formation of pyruvate. So we're going to start with this GAP, glyceraldehyde phosphate, that we ended the last one with. And remember, you're also going to end up with 2 of those. So they're going to go through a series of steps, and we're going to end up with pyruvate, and we're going to have 2 of those. So glyceraldehyde 3-phosphate goes under an oxidation reduction type reaction by using a dehydrogenase and a pyrophosphate, NAD plus, and a PI. So that's the NAD plus tells you that you have this oxidation reduction reaction, and you're going to end up with 1,3-biphosphoglycerate. And you can see over here, my pointer thing doesn't work very well, that the phosphate has now been transferred there and the hydrogen is gone. So that's why it is a dehydrogenase. This says intermediately, plus 3 delta G. Most of the free energy is going to be stored in this phosphate bond. Remember, we said they're high energy bonds, but this again is not a regulatory step. Step 7 then is to transfer this phosphate group from 1,3-biphosphoglycerate to an ADP. And remember, when you're transferring these phosphate groups, that's always a kinase. So we're going to have phosphoglycerate kinase, or PGK, is going to take that phosphate group and transfer it to an ATP. So this is when we're making our first ATP. And again, a kinase is what's moving the phosphate groups. And you can see here this has a large negative delta G. So this step, coupled with the step before, give still a large negative delta G, and the 2 reactions drive forward. Although this is still not a regulatory step, but our first ATP is made. Step 8 then is the conversion of this 3-phosphoglycerate to 2-phosphoglycerate. So you're just moving something from one place to another, so that's an isomerization reaction. And the enzyme is just a mutase. So this is phosphoglycerate mutase. It's just moving the phosphate from one place to another. Delta G is 4. It's not a regulatory step. It's just setting things up in the right position. Now we're going to have a dehydration of the 2-phosphoglycerate to phosphoenol pyruvate. And you can see this is an enolase. Enolase are enzymes that hydrate a double bond. So you can see on the left, there is no double bond between the 2 center carbons, but on the right it is. So this is what an enolase forms, the formation back and forth between breaking and making a double bond. And this one has a delta G of 7 as well. So this reaction is very reactive phosphoryl transfer species. The standard free energy of hydrolysis of the phosphoryl groups, we said before, those are high energy groups. So this now is PEP is a high energy compound. So what's driving these things? I had this up before. Again, these things are being driven by the glucose coming down the pipeline. So if there's a lot of it coming in, that's going to push this forward. So we finally get to the last step, is the transfer of a phosphoryl group from this PEP, phosphoenol pyruvate, to pyruvate. And again, if we're transferring a phosphate group, it's a kinase. So this is a regulated step. Increased levels of ATP will inhibit this enzyme. So if there already is a lot of ATP and you don't need to make more of it, then this will be an inhibitor of this pyruvate kinase enzyme. And you can see here the delta G is huge. It's minus 61.9 kilojoules. There's a lot of energy released by removing this phosphate group. It is a 2-step process, but overall it is large negative, so it's a spontaneously forward-moving reaction. And it is essentially non-reversible. So this step is a regulation step. It's a place where the cell can decide if it needs the ATP, it'll go forward, and if it doesn't, it acts as an inhibitor. Another inhibitor is fructose 1,6-biphosphate. It activates pyruvate kinase at an allosteric site. So I want you to go back and think about why that might be. And when I put up the slides for you to look at, you will see that I have the answer to that, but we're not going to do it now. I want you to think about it a little bit. Okay. So now let's look at the regulation of these pathways. So here are all the steps here on the right, and you can see these big jumps in large negative delta G's are like going over the dam. Some of the other ones are low, near equilibrium processes in here, but the ones that have the large negative delta G like this are the ones where you can't go backwards. For near equilibrium reactions, the flux can go back and forth. But these large negative delta G's, you can't go back and forth. And you can see the steps that happens. Step 1, step 3, and step 9 are clearly the steps that push the cascade forward, and they're not reversible. So again, we go from glucose to pyruvate in 10 steps. We needed 2 molecules of ATP. We needed a molecule of ATP to start it, but we also generate ATP to finish it. So this is the net equation, is that glucose plus NADH plus the 2 ADPs we started with end up yielding with 2 more ATPs and 2 NADHs. Okay. So looking over all the delta G's, and there's a cellular delta G, which is the delta G0, and like a calculated or in a test tube type delta G, but you can still tell which ones are large and which ones are small. So the flux of glucose through the glycolytic pathway is regulated to maintain nearly constant ATP levels in the organism. So this is adjusted based on the rate of glycolysis, or the rate of glycolysis, I should say, is adjusted by whether or not the organism or the cell needs ATP and what it has, and what enzymes it has, and what other enzymes are there. On a slightly longer time scale, glycolysis is also regulated by hormones, glucagon, epinephrine, and insulin, and by changes in the genes that express for these enzymes. But in general, it maintains a nearly constant level of ATP. An especially interesting case is the aerobic glycolysis in tumors. Tumors often carry out glycolysis at a much higher rate than normal tissue. And I suggested once before, this may be something you might want to do for your final project if anybody's interested in that. So glycolysis goes 10 times faster in cancer cells and tumor cells than in normal cells. And maybe you could use this as a way of detecting a tumor cell, or maybe kind of see if there's any way you could stop it and slow down the glycolysis in cancer cells and maybe defeat the cancer. All right, so far we've only talked about glucose, but obviously we don't just eat glucose. We eat all different kinds of carbohydrates and polysaccharides. So what happens to the rest of them? Well, we talked before about how the polysaccharides get broken down into the disaccharides, but then what happens to the disaccharides? Well, maltose has an enzyme that's called maltase that breaks it down into the 2 glucose molecules. And then the glucose molecules can just go through glycolysis just like the regular glucose molecules. Lactose, if you have enough lactase, will be broken down into galactose and glucose. Glucose, again, just feeds into glycolysis. Galactose is handled slightly different. We'll talk about that in a minute. And then sucrose has the enzyme sucrase, which breaks it into glucose and fructose. And again, glucose just goes into glycolysis, and we have to handle the fructose slightly different. So these other monosaccharides feed into glycolysis at different points. And I'm going to talk a little bit about some of these. So we said galactose feeds into the glucose 6-phosphate step. And what happens is that it takes a number of steps, including a kinase that adds a phosphate group onto galactose to make galactose 1-phosphate. But we really want to get down to glucose 6-phosphate. And what happens is that we don't really rearrange galactose to glucose. What happens is that there's another compound, a uridine galactose epimerase, which is an enzyme that has this uridine glucose on the end, and it does a transfer. It flips from one to the other. That's why it's called a transferase. It gives up the glucose and it picks up the galactose. So it transfers the whole molecule. And now you have glucose 1-phosphate, which can go to glucose 6-phosphate, and then just go on its merry way through glycolysis. So galactose isn't that really difficult to handle. But again, we need another kinase, we need an epimerase, and we need a transferase. And there are genetic diseases in which this uridyl transferase enzyme is defective, and that can lead to diseases and deficiencies in this enzyme. And this will come up in the text, and we'll see it in some of the workshops, and maybe again this could be something that people could do for a topic. Okay, so where do the other ones go in? Well, trehalose can be broken into glucose, and they feed into the same place. Galactose, mannose, all of them feed into different places on the steps on the glycolysis cycle, glycolysis chain. What I want to talk about though is these are just epimers, so they can be converted back and forth and then go into glycolysis, is fructose. Fructose enters glycolysis cycle in a different place, and that bypasses some of the regulatory steps and ends up being converted back to fat. So glucose is converted to fructose is converted into fructose 6-phosphate in the muscle by hexokinase, and it feeds in over here the glucose 6-phosphate, or by it's turned into glyceraldehyde 3-phosphate in the liver. But either way, you're down here. You've passed the regulatory step. So fructose is converted or feeds into glycolysis by 7 steps. You don't have to know any of these, but just know that it's a kind of a complicated pathway. And you can see that some of these pathways here involves glycerol 3-phosphate. These things start to sound a little like fats. So you can see where if it's not needed and you don't need the ATP, or you're not going through glycolysis, that this is going to go off into creating fats. So you can look at some of the things about fructose metabolism, is that fructose yields some of the same things, fructose 1-phosphate, fructose 6-phosphate. So some of it does go through. But if it doesn't go through, some of it bypasses the phosphofructokinase catalyzation step, and that's a major control point. So let me look at it this way. Where's the here we look at it this way. So we have glucose. Glucose is then broken down into the various steps through glycolysis, and when it hits this enzyme, this phosphofructokinase, is where it decides whether to go or not. If the body needs energy, needs ATP, it'll go forward and go through the rest of the cycle. If it doesn't, then it kind of backs it up and makes it go into glycogen and just stores it. But fructose comes in later. It bypasses this whole step in glycolysis and comes in later and just goes right into here. And when it gets here, if it gets here and the organism says, I don't need any ATP right now, then it just goes off and makes it into fat. So that's how fructose can end up being converted into fat. And that's some of the issues that people are studying now as to why high fructose corn syrup is not good for you. Because it bypasses this regulatory step of it being converted into glycogen, and instead is converted directly to fat. So a high fructose diet ends up having some of these health issues: insulin resistance, higher levels of triglycerides, decreased fatty acid oxidation because you don't need them, and it ends up bypassing some of the regulatory steps. It bypasses the insulin glucagon regulatory steps and just kind of jumps right into the middle. And we're going to talk about insulin and glucagon in a little bit too. All right, here's insulin and glucagon. So when you have an optimal blood sugar level, that's what your body is seeking to maintain, these tight levels. If glucose is taking into cells and stored as glycogen, everything is optimal. When you eat and drink sugary things, your high blood sugar goes up, insulin is released, and that causes glucose to be taken into the cells and then stored. If you're hungry, or when you first wake up in the morning, your blood sugar is low. If you've exercised or not eaten for a while, and glucagon is released at that point, and that takes glycogen out of your system and returns it into glucose and puts it into the bloodstream, because you want to maintain this blood level of sugar at an optimal level. And it's kind of a very tight range. So glucagon and insulin work on opposite sides of keeping. Opposite sides of keeping the blood glucose levels the same.